Last but not least, it's my pleasure to welcome Gustav Grieco. He will share some knowledge about how to get started with vulnerability discovery using machine learning.
Okay. Thank you. Thank you all. Thank you to be here. For you to be here. I know it's the last presentation that you should be tired. I can't promise it will be great, but I will do my best effort. Yes. I won't occupy the full 2 hours. That will be crazy. And in the I think in half an hour or something, I will give a break. So because the idea is to have some kind of workshop, but it's not completely mandatory to follow, because the tool I will present is something that we develop, and we need to explain to people why you should use it or why you can use it, and then people hopefully will use it. So this is it. Also, since what I'm going to explain is quite experimental, quite in development, you can ask any time stop me and ask for questions, not like the other talks. So if you feel lost or anything, just raise your hand and tell me I don't understand a damn thing of this, and I will try to rephrase or whatever. Okay, so let's start with the presentation. Great. So I'm a PhD student. I work in computer security, but as an application of machine learning. In fact, I work in a group of machine learning, so I'm kind of lonely there in the security part. So that's why I like to come to this kind of conferences. So this is a work we did in the institute. I work in Argentina, yes, because I'm Argentinian. I'm not Brazilian, just if anybody is asking. And we work in collaboration with people in France, specifically in an institute called Beremag in Grenoble. And well, it was a good experience. We this work is on revision for a conference, and we should have the results in a few days. Okay, so most of the talk will be motivation. The question is why you want to use machine learning for vulnerability discovery. Yes. So what are the objective of this talk? Is that you understand how you can use machine learning, and specifically for vulnerability detection, and that's in theory, and in practice how to do the prediction, the prediction and the visualization of the test cases with the tool which is called Discover. Yes. So let's try this. Okay, so first motivation and previous work. Can you see the C code? Yes? Okay, great. Who can tell me which bugs or vulnerabilities you can see in this trivial and very artificial code? One by one. So any suggestions? So let's take a quick look. Yes. We have someone. Yes. Sorry.
Arbitrary command execution.
Exactly. You can if you provide a large enough input one of the argument, you will have an arbitrary command execution, and I select this very simple C code. You can later try to compile and run it, because the stack protection won't help at all. Yes, if you manage to trigger the stack protection, yes, it won't help because you already execute a command. Yes. So any other thing that you see strange in this code? Okay, one trivial thing, if you don't put any argument, will crash because the argv will be null. Okay, no problem. So usually you call this program and it will supposedly execute something that it will be useful. But if you provide a large enough input, it would fail with a bash error saying, I can find your really long string of A's, and then you can do something, you can do bad stuff with this code. So the question is how you can usually find vulnerabilities in this, at least in this very simple example. So we have three main approaches. First, static analysis, in which we scan the code, yes, and we look for potential vulnerabilities. I say potential because since you are in the static level, you cannot really see what the code is really doing or can really do. So it's just imprecise. You cannot always know what the code will do. The other simple approach is dynamic program analysis, which will check the execution of the program, and when the program is trying to do something bad, will stop. Yes, like the stack protection of GCC, that it says, I see that someone is mangling with the stack, I will abort the program, and that's it. Yes. Of course, the problem with this is like you cannot examine all the possible executions. Yes, because usually you have infinite number of inputs. And finally, we have the testing using, for instance, a fuzzer, which will mutate inputs that you give, yes, or will generate new inputs in some cases. The problem with the fuzzing is that it's not, sometimes cannot be so effective because it could require many mutations to uncover interesting bugs, interesting vulnerabilities. So what we have here is the main problem that we try to tackle is like these approaches, they are not cheap. Yes, you need to have resources and time to use it. Yes, and the other problem is that we have a lot of programs, a very large amount of programs and reports of bugs that we want to know if we should fix them because they can be a source of vulnerabilities. Yes, for instance, in Debian, at least a few last year we have more than 30,000 programs and 80,000 bug reports and counting. I think now should be more than that. So let's try to see the concept of traces. So it's kind of a motivation to know if this kind of thing can help for the vulnerability prediction, for the vulnerability discovery and prediction. So what are traces? Just sequences of calls to functions, yes, standard C functions, with its arguments, yes, like, for instance, string copy, memcopy, malloc free. I know that you all know these functions, yes. And then the final state of the program. If the program exit, crash, abort, or just have a timeout because we cannot wait forever for programs so we have here 3 traces. Yes, the first one is with the root user that is supposed to find it. So there is a printf. Let's go back to the code a little. So we have here different functions: string copy, popen, fread, then the string, where I don't know how to pronounce it, printf, and finally pclose. Yes. So we can have these 3 traces. The second one has an invalid or inexistent user, and finally we have a trace with no argument that will crash. Yes. So you can see here that despite there is no there is no clear indication of a potential vulnerability here, there is some smell, something that we want to know. Yes, because, for instance, there is 2 string copies, but there is no string length. Yes, and that is not always something bad. But if you have to bet your money on this program, you probably wouldn't say that is something secure. Yes, you are copying something that you don't know the size. So that's something to see. Yes. So there is no clear indication, there is no direct evidence of a vulnerability here. Despite of that, we smell something strange in this code. Okay, so to try to focus this, what we are looking for in this article we develop and the tool. We try to have a technique to automatize or assist vulnerability discovery from traces, and from traces extracted directly in binaries, no source code. Yes. So a good thing is that if this program is dynamically linked, which is the usual stuff, we can easily hook functions. We can not just easily, it will be fast. Yes, because we can put breakpoints. Yes, in the function calls. Yes, and once you have breakpoints, you only need a few instructions to execute every time you hit these breakpoints. So the speed of the trace extraction surely nearly native. Yes. So a few key ideas. We have a large number of program and test cases to analyze. We want to learn patterns from a small sample, and then we want to try to predict if there's something going on in another program, in another test case. Yes, a good thing about this is like we already have the data. We have hundreds of thousands of bug reports. Some they come with a test case to reproduce. We have thousands of programs to analyze. They are just in your computers waiting to extract this data and start the prediction. So let's take a quick look to the previous work. This is something I like to do. I don't think that people create things from nowhere. So it's important to recognize the previous work. This is from a team in Germany. They create something called vulnerability extrapolation. And what they want to do, what they did, in fact, is they took a large collection of C source code. So they took some open source projects. They parse this C code and they extract API symbol functions and arguments and stuff like that. Later, they embed this this data into a vector space. This is a requirement for using machine learning. You cannot usually use machine learning with a source code like this. Yes, you can, because you need to have in a form of vector. That's how the machine learning techniques work. And then later, they try to identify the use of this API, and then to try to discover these new vulnerabilities, knowing that one of these points represent a function, a vulnerable function. Yes, this approach is somehow similar to the talk of the firmware, if you have been there. Yes. So what they could detect. So this is a vulnerability in FFmpeg from 2010, and they knew that the functions in gray are vulnerable to some buffer overflow or something. So you can see the function over there in the left, and you can see in bold which are the lines in bold. Yes. So it's not a stupid mistake of string copy some argument. It's something more subtle. So they knew that these two functions were vulnerable. Sorry, that the first function is flick the code frame 8 BPP. So they knew that this function was vulnerable, and they track which is the similarity with other functions in the same source code. And they later manually discovered that the flick the code frame and the BMD the code function has vulnerabilities. Yes. So this is good previous work. They use machine learning in the source code to get to assist vulnerability detection. Okay, but we want a different thing. We don't want to work with source code because we don't always have the source code. So the technique I'm going to present will be, it can be used for Microsoft Windows or another proprietary operating systems. So what is the general plan? What is the plan that they do and the plan that we want to do? First, we want to collect data. You cannot do machine learning with data. Second, you need to embed this data, yes, into the n-dimensional space. You need to transform data to these vectors, these numeric vectors. Then we need to do the model training and inference. And then later we can test this classifier, this predictor on new data. This is the general approach of all the machine learning, almost all the machine learning applications, and we cannot do anything without, usually without these 4 steps. Okay, so I'm going to explain this article that we wrote. It's called Toward Large-Scale Vulnerability Discovery Using Machine Learning. So, very simple explanation. We have the data set of test cases that we want to know if they are vulnerable or not. And we have some vulnerability detection procedure, like fuzzing, yes, or like manual detection. Yes, you can have a team of people working on vulnerability detection, like a security team, and you can get manually which are the test case in which they succeed to find a vulnerability and in which they not. And then, of course, the vulnerability detection process has an output, yes, which is just yes or no. Yes, they found something or not. So the idea is like this vulnerability detection procedure is very expensive, so we want something to bypass, yes, to predict. So we are going to extract features, to extract the data from the test cases, And we are going to use the output of the vulnerability detection procedure to train bdiscover. Yes, and then later we can predict if our procedure will find something or not. Yes, we cannot replace the procedure. Yes, we are going to predict, and if we found that it's likely to contain a vulnerability, we are going to use the procedure, because this technique will only say yes or no. It won't say the vulnerability is in this function, or as a buffer overflow with that. Yes, you need later to use this, yes, to confirm the cases that you find likely. But you can discard many of useless test cases. So that's the main idea. So any questions so far? Yes?
Basically, I'm interested whether you can use the same technique in order to generate inputs which are going to crash the program. So after you have discovered that you have a positive answer, whether you can, use machine learning to generate inputs that way.
So the idea that you are saying is like you train this, and then because you need to get the input from somewhere. Yes, because here there's no indication of where we collect this data set. But yes, we can use this procedure to close this loop. Yes, and to try to improve this. Yes, so in theory, yes, we are trying to develop this, but for this simple presentation, we are going to use only this procedure to select or to predict if a test case will be vulnerable or not, or likely. So the key principles of the tool: no source code required, so we can use it on proprietary systems. No human intervention to select features. This is really important because we don't manually select the features like in other applications. Manually selected features, manually selected data is usually better than the automatically selection, because a human can know some stuff about the data, but we want to focus only on the automatic selection. And then we want something scalable in the sense of we don't want to take a lot of time, a lot of resources to extract the traces. So we are not going to have instruction per instruction analysis. Yes, we cannot extract a data doing instruction per instruction. If you ever use GDB instruction per instruction, you know how slow it is, how terribly slow it is. Okay, so only breakpoints are allowed to get these functions, to get these traces. Right, so let's start with the data collection. Yes. So for this paper, we needed a data set. Yes, of course, otherwise we cannot say that our technique is good or not. So we took the Mayhem bag. I don't know if some of you remember. The Mayhem is a tool developed by the Carnegie Mellon University to do symbolic concolic execution. So they found the tool is not available. Yes, not even for me. We took the test case that the tool generated. Yes, test cases that were checked to be crashes or aborts or bad things. Yes. So we took these bags. Yes. That were about 1,000 in different packages, and every of these test cases has a crash report and all the required inputs that we need to trigger it. So we are going to see a little how these test cases are done. And we prepare a virtual machine, uninstall everything. Let's take a look to a test case. This is a small cross-assembler called XA for some obscure architectures. And the thing is that this program crashes, and it's still crashing in your computers if you install it. If you put these arguments, yes, the first argument /bo and some other stuff. So the tool found that if you put these 3 arguments, if you call the program with these three arguments, it will crash. Yes, we don't care of how the data is selected. We only care to use the data for the prediction. So this is one bug that we use to get the data for the training and later for prediction. So let's check how this bug still a bug. So you can start with GDB and the 3 arguments, and you can see immediately a segmentation fault. And if you see, just checking very quickly the registers of this crash and in which instruction is crashing. It's crashing in a null pointer. So nothing dangerous so far. I mean, this is not going to be a critical program, but still we did this very quick check to see how the program is crashing. So the question is, should we spend resources, so time, to try to mutate this test case? Are we going to find something interesting, some more interesting crash, some vulnerability, at least a small one, buffer overflow, or this kind of stuff? So the question is, yes, we should. So if we add a large amount of A at the beginning of the last parameter, it will crash in a different way. In fact, the buffer overflow check of the libc, if it's enabled in your system, will detect this because there is a string copy somewhere that is copying way over the limits, and it will be abort. So the question is, can we develop a technique that use this trace, yes, this trace with the crash, to say, hey, look, there is something funny about this trace. There is something interesting about this trace. I saw something before at some point to try to know if the fuzzer, a very simple fuzzer, will find this clear buffer overflow. Yes. So this is the main question that we try to that we want to answer. So well, it's a predictive approach in which we only need one memory corruption bug like this one, yes, to flag the test case as vulnerable. Yes. So once you flag the test case as vulnerable, you do other analysis later. Yes. But the question is, can we predict which test case will be vulnerable if we fuzz, I don't know, 100,000 times, because we don't know which mutation it will hit the right button. So the question is, can we make a prediction? Yes, and what data we should use? Okay, so let's go a little deeper into the XA assembly. I selected this program because it got clear vulnerabilities, so it should be easy to see. So here is assembly code. Since we already said that we don't want to work with the source code, there is a call to the getEmp function, and there are some operation, then some string copy, and then some other operations. So we can see from this assembly code that okay, we have move operation and all the stuff. We have some calls to the standard function from the the standard library function of C, standard C libraries, yes, functions. So these are one of the basic blocks of all the programs, yes? Because if this code was calling a library, any library that you can think, yes, later we don't know if other program will be using this library or not. But the standard C functions are standard and they are used in almost all the programs. So we are going to take them as basic blocks. Yes. So here is a small example of using ltrace. I assume that you know ltrace, and if not, it's very simple. You should use it to, if you want to know what is going on inside programs, it will just print which are the functions that the code is execute if the function in one binary are dynamically linked. Otherwise, you cannot know. And it will show you the arguments. If they are strings as strings, if they are numbers as numbers. And our tool, instead of taking the full parameters, it will take some labels. Yes. We call it primitive types. These primitive types are low-level types in the C programming or in the assembly code, let's say, in which, for instance, we have pointers and numbers. Yes. So a pointer can be a stack pointer, S pointer, a heap pointer, H pointer, or a global pointer, G pointer. And then we have null and dangling pointers, yes, that we can easily detect. And how we can know that they are that this argument should be a pointer? Well, we already know which is the interface of string copy. We already know that getM take a string. Yes, there is a list of this function with all the specification because this is standard. Yes, so we know where are supposed to be the arguments because we know the convention. Yes. So what we want to know is what we want to do, instead of using the full trace, we're going to use this trace with the primitive types. Yes. So the real reason behind this is that machine learning cannot deal with this kind of data because you cannot vectorize it. Yes, in the vdiscover output, we can vectorize because there is a set of values that we can have. Instead, in the ltrace output, there is also a finite set, but it's very large. Yes, you can have a number. You can have any number from, for instance, in 32 bits, you can have very large numbers, and it's really difficult to vectorize this into a space that the machine learning algorithm can use. So let's take a quick look to n-space embedding. This is going to be fast because this is just more technical stuff that is not really relevant. So because we just take the usual approach, we can do bag of words of these traces. Yes. Or we can do a new technique called word2vect, developed by Google, to map. So you can map every event in your trace to a vector. Yes, and then you can concatenate it. Okay, so we move from the domain of traces to the domain of vectors. Yes, as you can see. And then we can start doing some training. Okay, so before going into the detail, it's important to know that in machine learning, you cannot use the same data to train and test. This is absolutely wrong. Yes, if you do it, your results will be amazing, but it won't make any sense. So how people do to test the machine learning application on new data if they have a very limited supply of data, okay, they just select one part of the data to do the training and one part to do the testing. So they can always test on new data, and they do this several times without overlapping. Yes, and then later they average. Yes, later they average the errors that they have, and they have a final number. So formally, we split the data set in partitions. We use one partition to test and the rest to train. Okay, this is the standard, and you should never use the same data to train and evaluate your classifier. So later we use the usual techniques to do the training and testing, which are logistic regression, random forest, neural networks, and in the article is detailed which parameters we use, because according to the parameters you can have good performance or not so good, and stuff like that. So let's test on new data. So this is a figure from the paper. Yes. So this is called confusion matrix, and it will tell you more or less which is the how your classifier is actually classifying. Yes, and which of these classes, because we have two classes, flagged if the program was found to be vulnerable and we want to flag it, and not flagged if we don't want to flag it, because we know that it's not going to give any result to do the fuzzing. Yes. So if we have the flagged, yes, the predictor could manage to predict more or less half of the flagged test cases, of the new flagged test cases, yes, and missed 45%. And on the other way around, it managed to predict 83% of the not flagged test cases. So these are the test cases that you run your fuzzer for 1 hour and you find nothing. Yes, and apparently the classifier can more or less easily detect these test cases. Yes, and apparently it's not so easy to detect the other. And why? Well, the thing is that a vulnerability can have any form, any shape. Yes. So the code is arbitrary. You can have whatever you want in the code. So detecting vulnerabilities is difficult. Yes, it's very, very difficult. But if your code is failing because the original test case is not correct, is not the type of the input that your program accept, it tend to fail, saying there is nothing that I want here and stuff like that. So it prints an error or do some stuff that the classifier can easily recognize. Yes, and this is not a matter of looking for printf or not, because we don't select which are the features that we use. They are selected automatically. Okay, so if you want to know more or less how much you can save in your vulnerability detection process, you need to use the percentages of the vulnerable and non-vulnerable that you are of vulnerable programs or test cases that you are expecting. In real life, vulnerable test cases are a small part. Yes, because we don't see like everyday vulnerabilities everywhere. Yes, there are some programs that have them, and it's difficult to get them. So in fact, in our data set, 92% of the test cases are not vulnerable, and only 8% are. So we can do a weight average to compute from the ones that we predict that will be, which is the percentage that we actually hit. Yes, And the thing is, if you follow the numbers, you can see that to detect the same amount of vulnerable test case, just randomly selecting test cases to fast, you need to spend more time because your prediction is giving you some hints. It's not perfect, but it's giving you some hints. So it's actually more than 200 times faster. Yes. It's 2.7 times faster, 274% faster. So it's there is a gain in the classification. Okay, so if you have questions, I will give a short break, and then later we can do a little of the workshop part. Maybe 10 minutes break.
You said you extracted features by looking at C library function calls.
Yes.
Can you look at features that are not related to C library? For example, if, let's say, a kernel.
Sorry?
If you analyze a kernel which does not calls directly the C library.
You mean if I want to use this for kernel vulnerabilities?
Yes, or for something
instance,
that does not.
something.
Okay. Also, the training set was with the Mayhem.
Yes, exactly.
Bug list. You still have to have something for the other case. For example, you still need something similar for the kernel case. How would you go about it?
How
do you get the
it?
training set?
In the kernel, that depends on the type of vulnerability that you are looking for. Yes. If you are looking for, I don't know, buffer overflow, you just have to browse in the CVE list and say, okay, I have these particular inputs, these particular, syscalls, input to syscalls, because I guess that's what you mean, right? That the user do something and then the kernel fails, right? Okay, so you have to look at the list and manually select somehow. Yes, because in this kind of technique cannot give you the original data set. You need to collect it from somewhere else.
Yes, I understand.
Right? So later you can do the prediction if you have it.
Thank you.
Great.
So you chose this approach of listing the functions and then, taking, let's say, this into account when you build the, let's say, the vectors of, characteristics you're interested in. So you take into account the list of functions which are going to get called in the binary, right?
I use all the standard.
Yeah, no.
functions.
I'm curious whether you might choose a different approach. For example, let's say you use dynamic instrumentation framework, and then you take into account other things.
Sure. You can change the way in which you generate features. I mean the traces.
Yeah.
But we try to do as light as possible because we knew that the L-trace approach is fast. Yes. So that's more or less easy to run the program using ptrace and then get the traces. And that's it. But if you have another approach in which you can produce traces, you can just plug it into the tool. There is no need to use the features that I'm using. Okay. In fact, I'm going to show that the tool composed of two scripts. One is for feature extraction of the feature we define, and the other is for prediction, training and prediction. And you can use another features. We also experimented with static features. Yes, just classifying if the binary may contain some vulnerability or not, but this is too noisy for the data set that we have. That's it. But you can use other features if you want.
Thank you.
Other questions?
Okay, so let me see if I got this straight. You used that data set, the mayhem. Yeah.
Yes.
And those are all crashes. How did you generate your own not infected tests?
No, you need to, I mean, we took every of these test cases and we used a fuzzer, a simple fuzzer. Yes.
Okay, so the test cases that were not infected were the result of the fuzzer.
Yes, the idea here is like you have a crash, but you don't know if you can fuzz it to have a vulnerable one, a vulnerability or not. Yes.
Yeah.
So there is no normal programs. Yes.
Yeah.
This was made because sometimes when you develop, yes, you have a large amount of bugs and usually crashes, some aborts, maybe timeouts and stuff like that. So you want to give a prioritization. Yes, you want to solve first the one with the higher score and then the others. Yes. So in this first experiment, we only use the one from Mayhem. They're all crashes, but that's not a requirement. You can use any program. The program can finish with exit, and it will be the same. The classifier won't really look at the last condition. It will say, oh, okay, it's a crash, therefore it's vulnerable. No, it will try to use some of the parts in the middle, some of the events in the middle, to try to look for patterns. Yes, that's the idea. Later, we use a data set without crashing programs, and we have more or less similar results.
And regarding the class imbalance, you just dealt with that at the end when you weighted the scores?
No, we did it at the training, at the training stage. Because otherwise, if you try to train with 92% of one class and the rest won't work. I mean, most of the things, it won't work. So we did some oversampling, in fact. We oversampled the class, the vulnerable test case to have more data artificially.
Okay, thanks.
Okay. Okay, if you are still here, you are really brave because this is the last talk and the last part. Let's go into the next the workshop time. Okay, there is no requirement to do this on the computer. I'm going to show how you can use the tool, and then you can at home try it if you want. Okay, so one slide to show how you can install these examples. You can start a virtual machine, 32 bits, and then go SSH inside. You can clone the workshop examples and the tool, and you can easily install the tool with the two last commands. You enter into directly and do a user installation. Don't forget to add the path, so later you can just call. Oh, sorry. So the tool is open source. You can find it on bdiscover.org. It's written in Python too. It's using Python ptrace and scikit-learn for the training and prediction. It's composed by a few scripts. The test case creation, which is useful for this kind of dynamic traces that you collect. So you can have all the inputs that you need. The function feature extraction script and the vulnerability predictor, which will predict anything that you want. In fact, because it's just predicting from the data that you collect. You don't need to you don't need to be looking for vulnerabilities. You give some data and it will do the training and then later the prediction. So, and then BD is a script to save some time. Okay, so a very quick example on the traces that we can collect. Okay. Okay. Oh, it's going to be difficult with one hand. So I will turn off the microphone. So the idea, let's go into the, sorry. This is, okay, the terminal, let's go inside the directory. And we have here, we create a simple file and we use the tcreator script to create a test case. Yes. So a test case is just, directory that we can check out HTML test, and then you have a path to the binary that you are analyzing. Okay. Otherwise, hello? Okay. So here inside the input directory, we have the arguments that we need for this program, since we're required to execute user being HTML to text, and then the file. Yes, we are going to test with HTML to text as a program to trace. So this is very simple. You can play at home with different files, adding and removing from stuff. So the idea is like we can trace this very simply. So it's if extractor dynamic, and then the test case. Oh, dynamic. Sorry. So I just miss dynamic. Okay, so this will collect the trace. We can see just now. So there is one little time that you have to wait at the beginning of the trace taking, because you have to disassemble all the binary and put the breakpoints in the right point. So this is a trace. Yes, it's composed by the function call and the argument, which is in fact displayed in several words. Yes. So the idea is like, sorry. So I will go a little quickly. The idea is like we can do a trace. We can dump the trace to a file, and then later we can change the file that we are using for input and take another trace. And we're going to see that the trace is different. Yes, because we changed the input. So the trace should be probably different. But in fact, to visualize the traces is difficult because you see a large amount of function calls, and it's not the way. So the idea is later we're going to see how to do this visualization. But in the meantime, let's check this other example that we work that I did some months ago. I took Ubuntu image, and I select all the programs in users /user/bin. I install some packages like PDF processing tools, image processing tools, and stuff like that. So I collect all the possible binaries. Yes. For instance, identify that it will give you some information about images. And then later, I collect some files from the fuzzing project that give you one file for each type. One MP3, one text file, one zip file, one RAR file, and stuff like that. So the idea is like, I can use a simple program that is called manfuzzer to detect arguments, like command line arguments. And I can simply collect a very large amount of potential command lines. Yes? Some of the command lines will be invalid, but it doesn't matter. I will use them all, and I will try to fuzz the inputs in, for instance, the WAV file that I'm sending. So a question will be, if I have a PDF program that extracts PDF and show text, how a WAV file will do? It won't do anything good. Yes, it will stop very early in the program. But it doesn't matter. We are going to use this for training, because in some cases we are going to fuzz and we are going to find a crash. Yes. So the question is, can we select? Can we predict which of these command lines that we fuzz using a simple fuzzer, which is called ZZUF. I don't know how to pronounce it, but so we did this, and we got some crashes, some aborts, some timeouts, some interesting test cases that we want to try to predict. So in fact, what we did is we passed through bdiscover, and we got similar results. Yes, you can see in the bdiscover website, you can see a detailed process of this experiment. Yes. In fact, here in this workshop, I put some. I don't know why I can't. That's it. So I included some of the data set. No, it's data set. So you cannot see a lot. So we have 3 files here. We have 3 files. The command file, in which you can see all the test case, is very large, 64,000 command lines. And then the traces is just a sample of the traces that you can have, yes, in which half of them are detected as buggy, has some crash, some abort, some interesting bug, and the other is just nothing bad, exit with some code. So the question is, can we predict in this more realistic example? Let's take a quick look to the commands that I was using. So if you try to fuzz the SHA 256, it won't crash because it's just counting the bits. But in fact, I have PDF to text and all kind of programs here. Ruby, GDB, all kind of things here. So in fact, all these test cases are different. They have different command lines. So the question is, can we predict which of these test cases are going to crash? And the answer is yes, you can. Yes. So as a simple demo, I took this data set, I split in one part of train and one part of test, yes, and run it on this netbook, and I got around 77% of accuracy. I can run it again, but it will take approximately 7 minutes to do the training. This is a netbook, so it's. I mean, I can show you, but we will just wait for 7 minutes. So the idea is like later we can do the prediction, and if you have the test parameter, if you have the test parameter, you can if you have the correct class for every example that you are predicting, you can see which is the error, the accuracy. So finally, I want to show, and this is probably the most interesting thing to see, is that you cannot only train and predict, but you can also visualize test cases. And this is really interesting because you can just get all the files that you want to execute one program with a lot of files, and you want to see which are these files, which are these inputs are similar in the trace, which generates similar traces. So what I'm going to do is I'm going to plot. So it's vPredictor, yes, cluster. So cluster, bag of words, dynamic. What I did is I just use the file program, which selects, show you in screen, which is the type of the file. For instance, MP3, and give you some information. If you execute file with different types, different type files, it will show you different messages. It will show you, for instance, for an MP3, which is the duration, the encoding, and all the stuff. So the thing is that we can simply use these traces that I already collect. This is seeds, right? Sorry. Seeds, and I put it here, file traces. No, here I need to put, here, sorry, dynamic, where I put, here, sorry. So this will vectorize these traces, and it will show you here. So this is a map of the traces. This is the most interesting part, because you can see that all these traces, we can do some exploration. For instance, this cluster that is here. Here we can see that these traces can group together some type of files, because the trace looks similar. And if the trace looks similar, the input that generates this trace should be somehow similar. This depends on the program, of course. In this case, file just print the information of the file, the type of the file. So you can see that some of this compressed file here, for instance, gzip, tar, 7zip, cav, sed, there are some outliers like WAV, for instance. But in general, we can see that the prediction, that the clustering here is giving you information. Imagine if you have a new type of file that you don't know what it's doing, but you have a lot of test cases. So you have this new type of file that you don't know, and a program to parse them, and you can cluster these traces because you don't even need the source code. You can just execute and get the traces. And what you can do is you can get a map, yes, of similarity. And this map can be very interesting from the fuzzing point of view, because instead of fuzzing all the files here, all the files here, I can maybe fuzz one or two. Yes, because they are similar in some sense. So they are probably using the same part of the code, using the same functionality. Yes, so we probably want to do this. And also think that if you produce a mutation of one of these files, this mutation will be like an arrow, because a trace of a mutated a file will be probably in a different point. So an arrow will be a mutation. So maybe if you combine this, you can have a map that you can somehow navigate with your mutations. Yes, and this can be a good starting point for what you said about how to change the input to have new stuff in the fuzzing process. Well, so this is more or less what I wanted to explain a little more, to show a little more of examples, but I think we are all tired and it doesn't make a lot of sense to continue with the examples in the computer. So if you have any questions, okay, I can give you, okay. Oh, I shouldn't move from here.
Okay, so in the first part of the presentation, you said you looked into logistic regression, random forest, and neural networks, but you only showed a percentage for one of them. Which one was it?
The best, it was random forest.
Why do you think that was it? It was because you used Word2Vec, or?
No. This example was bag of words. Yes. The thing is that this dataset is very noisy, it's very difficult to classify, and random forest is the most robust thing ever. And usually neural network has a lot of parameters, and you don't have usually enough time to explore them. So it's a matter of, oh, this is working more or less, okay. We don't have to try so hard for the first article, for the first idea that you want to develop. So that's it.
So your intentions were to throw away the examples that weren't producing you bad stuff and try to improve the score of the anomalies?
Yes. At the end of our research was that. At the beginning it was, oh, let's predict, let's do amazing stuff. But then you start to realize how the classifier could be classifying, and that's it. Okay.
The results that you showed showed a lot of false positives.
Yes.
In the classification, and similar with WAV files, file classified or identified as
here
archive in this cluster.
Yes, on the cluster you said.
Yes, the example that you showed.
Yes, there are some misclassification, but in fact there is no classification here.
Yes,
it's just clustering.
It's just I understand. My question is, what are your next exploration ideas to reduce the false positives?
To reduce the false positives, we don't know if it's possible. I mean, you can change, you can use other features, you can improve these features with more information. We have some ideas of taking, instead of a trace, a graph. Because in fact, I show you a trace, yes, but since you have pointers, you can know that you have like a malloc, and then you use the return pointer to feed some string copy, right? So in some sense, you have a graph. If you know that this particular pointer goes to this particular string copy, so you can create a graph of this and try to feed your machine learning, your clustering with that, and it could give you some differences that maybe is confusing the classification. And also remember that this is bag of words. It's the most basic thing that you can do, and for this is working pretty good for a really simple approach. So there are some other things that we are thinking to do.
And another question, how can you use this program or another approach to direct you more precisely to the problematic part of the code, instead of only just saying you this has high probability of crashing or
well, the answer is we don't know, but there is one possibility, which is taking subtraces. Instead of all the trace, you can take like a window that you slide. So when you find something interesting, you can flag it. So for every trace, you can have several places in which you see some stuff. Yes, and then if you know how to map this into the code, because these calls are related in some part of the code, you can go back. But this can be very complicated to map into the because programs can do anything. Yes, you can have a function working properly that is called in a way that it makes everything, that is overwrite everything, and it depends on the code. So this is usually very difficult to do. But yes, it's obviously what we want. We want something that tells, okay, you should look here and not in all the program, all the possibilities.
Okay, thank you.
Okay.
Are there any more questions?
Okay. Okay, thank you for listen until the end. I know it's late, and we are probably tired, so that's it.